Welcome to Beyond the Brackets. Today we'll continue our discussion on particular integrals of type 2 where the right hand side contains sin ax or cos ax. For this, the substitution is d square is equal to minus a square because the second derivative of sin or cos gives minus a square times the function. Other than sin ax or cos ax, sometimes the RHS contains terms like sin a cos b, cos A sin B, cos A cos B, sin A sin B. These products must first be converted into sums or differences using trigonometric identities. Like 2 sin A cos B will be written as sin of A plus B plus sin of A minus B. 2 cos A sin B will be written as sin of A plus B minus sin of A minus B. 2 cos A cos B will be written as cos of A plus B plus cos of A minus B. And 2 sin A sin B will be written as cos of A minus B minus cos of A plus B. Besides sin ax cos ax, these trigonometric expressions also fall under type 2 since they can be expanded into sin kx and cos kx. The first question is already given in the operator form. The auxiliary form is given by replacing d with m and equating it to 0. So we get m square plus 3m plus 2 equal to 0. The roots for this equation are minus 1 and minus 2 which are real and distinct. Complementary function for this is given by yc is equal to c1 e power minus x plus c2 e power minus 2x. Particular integral is given by 1 by operator form into RHS. Since RHS is sin 3x which is type 2, we substitute d square is equal to minus a square. Here a is equal to 3. So we get sin 3x divided by minus 9 plus 3d plus 2 which is sin 3x by 3d minus 7. The denominator contains d and in type 2 we substitute only for d square. So we rationalize the denominator by multiplying and dividing by 3d plus 7. Solve the denominator first before moving on to the numerator. So again d square in the denominator will be replaced by minus a square, that is 9 into minus 9 minus 49, which is 3d plus 7 into sin 3x by minus 130. The denominator is simplified. Moving on to the numerator, we have 3d plus 7 multiplied by sin 3x. We know that the operator d represents differentiation. So 3 into differentiation of sin 3x will be cos 3x into 3 plus 7 into sin 3x. The solution is given by y is equal to complementary function plus particular integral. So y is equal to yc plus yp. The next question is again in the operator form. Its auxiliary equation is obtained by replacing d with m and equating it to 0. We get m square minus 4m plus 3 is equal to 0. The roots of this equation are 1 and 3 which are real and distinct. The complementary function yc is equal to c1 e power x plus c2 e power 3x. For the particular integral, we get 1 by operator form multiplied by the RHS. Here the RHS is of the form sin A cos B. Using the identity 2 sin A cos B is equal to sin of A plus B plus sin of A minus B. Substitute A is equal to 3x and B is equal to 2x. So 2 sin 3x cos 2x will be sin of 3x plus 2x plus sin of 3x minus 2x, which is sin 5x plus sin x. Since the RHS has two terms, sin 5x and sin x, we'll evaluate the particular integral for each term separately, which gives 1 by 2 into sin 5x by d square minus 4d plus 3 plus sin x by d square minus 4d plus 3. The first term, sin 5x, is type 2 where the substitution will be d square is equal to minus a square where a is equal to 5. So we get sin 5x divided by minus 25 minus 4d plus 3. For the second term, sin x, again it is of type 2 where the substitution is d square is equal to minus a square where a is equal to 1. Replacing d square with minus 1, we get minus 1 minus 4d plus 3. The terms simplifies to sin 5x divided by minus 22 minus 4d plus sin x divided by 2 minus 4d. Notice that there is 2 common in the denominator, so we take it out to make the calculation easier. The expression becomes minus 1 by 4 sin 5x by 2d plus 11 plus sin x by 2d minus 1. Now each denominator contains only d, but in type 2 we can substitute only d square, not d. So we rationalize the denominators. So the first term will multiply and divide by 2d minus 11. For the second term, we multiply and divide by 2d plus 1. Numerators will be kept as it is while we solve the denominator. For the first term, the denominator is 4d square minus 11 square. For the second term, the denominator is 4d square minus 1. The first term has sin 5x, which is type 2, for which the substitution is d square is equal to minus a square, where a is equal to 5. So substituting in the denominator, we get 4 into minus 25 minus 121. For the second term, you have sin x, which is type 2. Again, the substitution will be d square is equal to minus a square. Here, a is equal to 1. So the denominator becomes 4 into minus 1 minus 1. Now the denominators are simplified, so we move to the numerator. 2 is constant. Differentiation of sin 5x will be cos 5x into 5 minus 11 into sin 5x. For the second term, again 2 is constant. Differentiation of sin x will be cos x plus sin x. Taking minus common for both the terms gives the particular integral. The solution is given by y is equal to yc plus yp. Substituting both the values completes the solution for this question. Next question is again in operator form. Its auxiliary equation is given by replacing d with m and equating it to 0. So we get m cube plus 4m is equal to 0. The roots are given by 0 and plus or minus 2, where 0 is real and distinct, for which complementary function will be c1 e power 0x. Plus or minus 2i is complex root. We know that for the complex root alpha plus or minus I beta, complementary function is given by e power alpha x into c1 cos beta x plus c2 sin beta x. Here alpha is 0 and beta is 2. So we get c2 cos 2x plus c3 sin 2x. Particular integral is given by 1 by operator form into RHS. Here the RHS has two terms, 5 and sin 2x, where 5 is type 1 and sin 2x is type 2. So we separate both the terms and solve them individually. The first term 5 can be written as 5 into e power 0x, which is type 1, where a is equal to 0. Here we substitute d is equal to a, so we get 5 into e power 0x by 0, which is a case of failure. In this case, we multiply the numerator with x, differentiate the denominator, and then substitute d is equal to a. So we get x into 5 into e power 0x divided by differentiation of d cube will be 3d square, differentiation of 4d will be 4. Again substituting d is equal to a, that is 0, we get 5 by 4 into x. For the second term sin 2x, which is of type 2, the substitution is d square is equal to minus a square, where a is equal to 2. Replacing d square with minus a square, d cube can be written as d into d square plus 4d. So we get d into minus 4 plus 4d, which is 0, and it is again a case of failure. We multiply the numerator with x and differentiate the denominator. We get x into sin 2x divided by differentiation of d cube will be 3d square and differentiation of 4d will be 4. Again, in place of d square substituting minus a square, that is minus 4, we get 3 into minus 4 plus 4. So the particular integral is 5 by 4 into x plus x sin 2x by minus 8. Solution is given by y is equal to yc plus yp. Substitute the values and that will be the answer. Here some practice questions are included along with their answers.